Okay, so we finished with the Ekman layers, and the important thing of the Ekman layers that we will see today again is the solution of the vertical velocities at the edge of the Ekman layers at the top and at the bottom. Why are you laughing? Because of the Easter. So today we'll start with the first theories of the wind-driven gyres, wind-driven circulation. Okay, so if you remember that picture of all those arrows that I show you at the beginning, those wind-driven gyres that appear in the North Atlantic, South Atlantic, North Pacific, South Pacific. Indian Ocean there's only one because there's no north side of the equator, Indian Ocean. So all those gyres they all look slightly different in every different basin, but they all look very much alike because they all obey the same dynamical system and the same model. Okay. And so basically we will see that they are composed of an interior solution in geostrophic balance and an Ekman layer at the top. And what the Ekman layer does is transmit the input of momentum from the wind stress to the interior of the ocean, to the geostrophic flow. And the geostrophic flow will start to respond in a certain circulation. And that response is the same in the North Atlantic, South Atlantic, North Pacific, and South Pacific. That's why they all look very much alike. They're slightly different because the geometrical setting is different, but they all very much look alike. So we will use the two solutions, the geostrophic balance for the interior and the Ekman layer at the top. And then we will see that the ocean will respond in two different ways. So there will be an interior solution where the ocean will respond in one way, and it will be a boundary layer correction, a horizontal boundary layer correction. Okay? And that boundary layer correction will respond in a different way to the input of momentum. Okay? So as we were looking at the Ekman layer, we had a geostrophic flow and a boundary layer correction in the vertical. That was the Ekman layer. Once we put together the Ekman layer on top of a column of the ocean in geostrophic balance, the total column of the ocean will respond as an interior solution plus a boundary layer correction on one side of the basin, at the east and on the west, where the ocean will respond in a different way. And we will see why. Okay? So we will start with the, as it happened in history, chronologically, the model was built from a very simple model to a much more complicated model, and actually a very logical way of adding complexity to the model. Okay? So we will start with this very simple setting. It's a nice diagram I'm very proud of. So we'll see that we will use a flat bottom. Did you all get the notes? Yes? Okay. As I said to him, I forgot to write on the email. It doesn't matter if you did, but don't print the notes. I'm sure you all printed the notes. Okay. Because every evening before preparing the class, I revisit the notes and I say, oh, I find a mistake. I add a figure. I add a sentence. Okay. Nothing major. So if you printed the notes, it doesn't matter. Okay. But so every time I do a change, I upload on the Dropbox folder the new version. Okay. But it's always like a typo, or last night I added a figure. Okay. So you can see it on the new version. So the simplest setting, we will use a flat bottom, as you see. The inclusion of a variable bottom will change the solution slightly. Well, very importantly, on the sides of the basin. But we'll start with a flat bottom. We will start with steady state. Okay, we're interested in the steady state solution. We're not interested in the time varying solution, although we will see the solution for the variable solution as well. And we will use the beta plane approximation. Okay, I'm sure you've seen the beta plane approximation in atmospheric dynamics, but I don't know if you got a derivation of the beta plane solution. Even if you did, I'm going to do it. Okay, So we will do the derivation of what is the beta plane approximation, okay? Which myself, I always when I was a student and when I started working, I used the beta plane approximation, but I actually myself never derived the beta plane approximation. And when I was preparing these notes last year, I did, and I thought, oh, nice. It's actually very simple. But you know, you get the solution. This is the beta plane. Beta has to be much smaller than f naught. Okay, but how you actually get there is very simple. Okay. So we'll start with the reference system that we have. Okay, this is our Earth. Okay, with the rotation omega. This is what we're going to call Z. Here we have K omega sine of theta. This is theta naught. Yep. Oh, this is the angle theta. Now we're going to draw a plane. Z equal naught. Okay, so that's the plane where we will work on the beta plane. This is going to be y. Zeta is equal to 0 and x is into the board. Now this point here, this is A, the radius of the Earth, and this point here is A tan of theta minus theta naught. Yes. Okay, so that's the geometrical setting. So we will derive the beta plane on this plane Z equals 0. So why is the beta plane approximation useful, and why we use the beta plane approximation useful? Because we want to avoid the sphericity of the Earth, all those extra terms involving working on a spherical system, and we want to work on a Cartesian plane. So this plane Z equals 0 with y and x. So we want to work on a Cartesian plane, but we want to retain the effects of the sphericity of the Earth. Okay? So we want a simple setting, Cartesian, without sphericity, but we want to retain the effects of a sphere. So we're going to work on the plane Z equals 0, which is going to be the beta plane, and it's tangent to the sphere, okay, with radius A. So this point, A tan of theta theta naught, the beta plane approximation is going to be valid for relatively small variations in theta in the latitude, okay? And so for relatively small variations of latitude, theta minus theta naught is relatively small. So this can be approximated to A theta theta naught, because the difference theta minus theta naught is relatively small. So this approximation is going to be valid for a few thousands of kilometers. Okay? If you walk on a plane that goes from the equator to the pole, the beta plane approximation is not valid anymore. Okay? So our Cartesian coordinates are y equal, so that y, A theta minus theta naught. Okay? So this is our meridional coordinate. Then we have z, which is r minus a. So r is the distance of wherever you are to the center of the sphere minus the radius. So it's giving you the distance from the beta plane. So z is r minus a. A is the radius of the Earth. and x is phi minus phi naught, the longitude, times the radius times cosine of theta naught. So this is going to be the Cartesian coordinates that we're going to use. Okay? So the important thing is that with this approximation for small variations in latitude, there is a linear relationship between the latitude and y. Okay? So tau, so this is our Cartesian coordinate. So tau is going to be equal to tau naught plus y over a. Okay? So there's a linear relationship between the latitude and the meridional coordinate in the Cartesian plane, which is what makes this system extremely useful. So we said that the variations in latitude are small, and so we can approximate sine of theta that we will use in F, planetary verticity, as sine of theta naught plus cosine of theta naught y over a as a truncated series of theta latitude using this. Okay, you do a series and you truncate it using tau from this expression, and this is what you get. So if you use sine of theta as that truncated series around theta naught, then you can rewrite your Coriolis parameter f, which used to be sine of theta, right? But sine of theta, we know what it is. Sorry. Omega. Sine of theta. But now we're going to use the approximation of sine of theta. So it's going to be 2 omega sine of theta naught plus 2 omega over a cosine of theta naught y. Okay, so this is the approximation of f, the Coriolis parameter, using the beta plane approximation. And what is that? This is nothing but f naught plus a parameter that we're going to call beta, where beta is 2 omega over a cosine of theta naught y. Okay. So this is beta. Okay, so this is the beta plane approximation that we derived using a Cartesian coordinate and relatively small variations in latitude, theta. Okay. But what is beta? Beta is the meridional gradient of f. Okay. And it's very important because by using beta, so you have f naught, which is a constant, because t naught is a constant. Okay, so f naught is a constant, and then you use beta, and beta is a function of latitude, and now latitude is y. Okay, so beta is a function of latitude, so beta is what is giving you the information of the sphericity of the Earth. Okay, whereas f naught is just a constant. So beta is what is going to retain in our equations the fact that the Earth is a sphere and is a dependence on latitude. What is beta? Beta is the gradient of the meridional gradient of f. In fact, if you do df by dy of theta at theta naught, which is where we're working on, if you do the meridional gradient of that, and if you use the linear relationship, that is df a d theta at theta naught, and this is 2 omega over a cosine of theta naught. Okay, so beta is nothing but the meridional gradient of the planetary vorticity. And so is what is giving you the meridional dependence on latitude of all the equations that we're going to use. Okay, so you're probably saying the beta plane is f equal f naught plus beta y, but this is where it's coming from. What are typical values of f and beta? You probably know. This is the nice diagram. Again, it took me more time to do the diagram than the notes. Typical values of f is typical value. Minus 1. Minus 4. 10 to the minus 4. 10 to the minus 4. And beta? Do you know? Minus 7. Don't look at the notes. 10 to the minus 11 is the meridional gradient of f. It's going to be much, much smaller. And if you actually see the plot I made last night, that you don't have on your notes, okay, it's this very nice plot, extremely beautiful. You have f on the x-axis, 2 omega sine of theta. On the y-axis you have latitude from the equator to plus 90 degrees, okay? And this is how f, the blue line, varies as you move towards the North Pole, okay? From 0, linearly increases until 50 degrees north or something like that. And then because of the sine of theta, which is a value of 1.4 or something like that. So for typical mid-latitude values, where's the stick? Yes, thank you. So for typical mid-latitude values, let's say 40 degrees, f is around 1, 10 to the minus 4. And this is beta. Beta is the meridional gradient of f, okay? So it goes from a maximum close to the equator, where the meridional gradient is maximum, to 0 at the pole, as this approaches a constant. Okay. So again, for typical mid-latitude values, 40 or something like that, theta is 1, 1.5, 10 to the minus 11. Okay. This is what f and beta look alike. My mom is arriving tomorrow. Okay. So we have the beta plane approximation, f naught plus beta y. Okay. And this is only valid for large enough areas where you need to feel the sphericity of the Earth, but not too big. Otherwise, the beta plane approximation is not valid. Okay. So this is valid only when beta y is much smaller than f naught. Or, of course, beta y over f naught is much smaller than 1. Okay. Beta has to be smaller than f naught. If you study a region that, or if your region of study doesn't change much in the meridional direction, so you're not interested in the meridional variations and the effect of the sphericity of the Earth, then you can use the f-plane. I don't know if you came across of the F-plane, but the F-plane is nothing but F equal F naught. Okay, you forget about beta. There's no beta, there's no meridional dependence on your dynamical equation, on your dynamics, on your horizontal momentum. So you can just use F as a constant. Okay, so remember these are the simple approximations that we're going to use to derive the first solution for the wind-driven gyres. So a flat bottom, we will put topography. Steady state, we will see the solution when there is no steady state, but we will not use it. And the beta plane approximation to work on a simple Cartesian plane, but retain the sphericity of the Earth. Okay, so now we will derive the first solution for the wind-driven gyre, and fine. Keep looking at the plot.
I'm wondering what's happened at the equator.
Well, sin of theta. That's just a numerical. I started from 1 probably, 1 degree instead of 0. That's why. So we'll derive the first solution for the wind-driven gyre, and so we'll start with the and we'll derive what is called this Virchow balance. Okay. So we'll use the beta plane. And with the beta plane, if you remember the geostrophic equation, but using the beta plane, is going to be minus F naught plus beta V y. Okay, it's just the geostrophic equations, but using the beta plane approximation. And then we have the hydrostatic balance. And then we have mass continuity. Okay. So these are the simple setting of the equations. Now if you cross differentiate the horizontal momentum equations, so the first and the second, cross differentiate, so you do d by x of this minus d by y of that, you will end up with that is equal to 0 plus beta. Okay, d by x of this minus d by y of this, pressure gradient terms vanishes, d by y of this, so you have beta v, which comes here, and then you have f naught of du by dx plus dv by y, and you have beta y of du by dx plus dv by dy. Okay. But remember that we are doing the beta plane approximation, and in the beta plane approximation, the beta terms must be much smaller than f naught. Okay, that was what we said before. In order to be valid, beta must be much smaller than f naught. So this term must be much smaller than this term. So we can neglect this term. And now we can rewrite this as and then the F naught. Okay, this is minus d by dz of w, and we put it on the right side. So this is the solution of the Jostrophic. Remember, we were using the Jostrophic equations with the beta plane approximation, and we got to that solution. And this is what is called the Svarogin balance. So remember that when we are using the Jostrophic equations without beta, the vertical velocity was equal to 0. Okay. There was no vertical velocity. We just had horizontal components of the velocity, and the vertical velocity was equal to 0. We could find the vertical velocity only in the Ekman layer. Now, by introducing beta, we find that we have a vertical velocity and a vertical derivative of the vertical velocity in our solution. And what this solution is telling us is that if there is a vertical velocity, imagine a fluid column, we have a vertical velocity, okay, and that fluid column might shrink or stretches, okay, because of the vertical velocity. And as it stretches, for example, then it has to shrink okay, in order to conserve angular momentum. Okay. So you're just trying to conserve angular momentum, so if you stretch and then you shrink, then you have to rotate faster in order to conserve angular momentum. But we'll see that there's going to be two responses in the ocean, one in the interior and one on a boundary layer correction. Okay. So in one case, the relative vorticity, so the rotation of the fluid column, will change, and in another case, it's not going to be the relative vorticity to change, but it's going to be the planetary vorticity to change and balance the change in the stretching or squashing of the fluid column. And this is what the Svarogin balance is telling us. If there is a vertical velocity, okay, that shrinks or stretches the fluid column, that will be balanced by a change in the planetary vorticity, the meridional gradient of f, beta. Okay? So if we have a vertical velocity, that will be balanced by a change in the planetary vorticity. And that change in planetary vorticity is associated with the meridional velocity. Okay? So the basic picture is that if you squash the fluid column, so vertical velocity is downwards, you squash the fluid column, what is going to happen? The fluid column is going to start to rotate faster or slower? No. What is going to happen is that the fluid column will start to move and change f, and it's going to move towards the north or it's going to move towards the equator, depending on if the fluid column has been shrunk or stretched. Okay. And so it will move meridionally in order to balance the vertical velocity, and it will do that by changing beta, which is the meridional gradient of f. So it will go towards the pole or towards the equator. And that will be associated with the meridional velocity. So you're moving towards the equator or you're moving toward the pole. Okay. So that's the response. That's the response of the large-scale ocean circulation. This vertical velocity obviously is coming from the Ekman layer. Okay? So if you have an input of momentum at the surface, for example, the wind stress, that creates an Ekman layer, and that Ekman layer has a vertical velocity at the edge. That vertical velocity will start to talk to the interior, to the geostrophic part of the ocean. Okay? The geostrophic part receives a vertical velocity. The fluid column is squashed or stretched, and that is going to be balanced by the whole fluid column moving towards the pole or towards the equator by changing beta. And that movement is going to be a meridional velocity. Okay? So the whole ocean, this is the first solution, will move towards the equator or towards the pole. Okay, so now we can study what this vertical derivative of the vertical velocity is. So if you take the vertical derivative of this horizontal equations, okay, just taking the vertical derivative of the horizontal momentum equation with the beta plane approximation. But remember that we have the hydrostatic balance, so dP by dz is equal to 0. And so this means that du by dz equal dv by dz equal to 0. There's no vertical derivative in the horizontal momentum. It is a homogeneous interior where there is no vertical derivative in the horizontal momentum. We're just looking at, let's say, the integrated solution. Okay. So the whole fluid column will move the same way. We are outside of the Ekman layers, and it's a homogeneous integrated vertical column where the whole column will move in the same way. So this means that z is a constant and is not 0. Okay, so that's why we're using a very simple setting, that schematics with a flat bottom. It's a homogeneous ocean where the horizontal velocities don't have a vertical derivatives. So what is this? You take the vertical derivative of that, and remember it's a simple homogeneous ocean, so you have vertical velocity at the top minus vertical velocity at the bottom over the fluid column H. Okay? And if you remember the Ekman solutions, which is the only thing that matters here, the vertical velocity at the edge of the top and bottom Ekman layer, this is 1 rho over F naught of the curl of tau over H minus D over 2 the vorticity of the geostrophic flow, right? That was the over H. That was the solution of the vertical velocity at the edge of the bottom Ekman layer. Now you need to take the geostrophic expressions for the horizontal velocities. And you take the derivative of those, 1 minus rho naught F naught, and du dx. Yes, you take the horizontal derivative of those. And now you plug that solution in here. So beta V F naught.
Sir,
Yes?
please, the du, is it du dy or dx?
Du dy. Thank you. do the horizontal derivative of the velocities? I don't remember, let's see. So this is going to be beta. And what is V? V is 1 over rho naught, F naught, dp by dx. Forget about this for a second, I don't remember why I did it. So you replace V with the geostrophic expression for the geostrophic meridional velocities, which is this, equal F naught, but we move F naught on the left hand side, so F naught squared. So du by dz is 1 over rho naught F naught H, the curl of tau, minus d over 2h, but then you replace, that's why, the vorticity of the geostrophic flow is going to be dv by dx minus du by dy, so you put the expression, and so you put this rho naught F naught, and okay, the vorticity of the geostrophic flow. So this is rho naught, F naught, F naught. So you have beta dp by dx equal F naught over h. Okay, you move this F naught on the other side of the curl of tau minus d over 2 of Laplacian of b. Okay, so this is again this virtual balance, but after replacing the expression for d by dz of the vertical velocities. So this is what is giving you the meridional velocity. Okay, in geostrophic balance, dp by dx, you have a pressure gradient and you have a geostrophic velocity. This is the contribution from the top Ekman layer, the curl of the wind stress, and this is the contribution of the bottom Ekman layer, where the vorticity of the geostrophic flow was coming into place.
So the Laplacian is for the horizontal.
This,
The Laplacian is just for the horizontal.
yes, you have the geostrophic flow. The vorticity of the geostrophic flow is the dv by dx minus du by dy, right? Which is why I was doing this. So this is this vertical balance. You have a vertical velocity, and that vertical velocity is balanced by a change in the planetary vorticity, not relative vorticity. And that induces a meridional flow. What is this vertical velocity? Take the beta plane, and you know that the horizontal components of the velocities are constant throughout the column. You look at the vertical velocity, you take the solutions from the top and bottom Ekman layer, which is the curl of the wind stress and the vorticity of the geostrophic flow. You replace that into this vertical balance, and this is what you get.
Yes, sir.
Yeah.
Why do we replace the meridional velocity with dp over dx? Because we prefer having a scalar pressure.
Because because it's just another way of seeing it. And because dp by dx gives you the idea of a geostraphically balanced flow. But this and this are equivalent. Of course. Okay, so this is the Sveggio balance, which perhaps you've heard of it already. But now the Sveggio balance is not enough because there's no way you can work with just the Sveggio balance. Okay? And this is where Stommel, the very famous Stommel, came in, and he added a very important piece to the Sveggio balance, which makes it more tractable. And it's probably the first solution of the wind-driven jar. This is not a complete solution of the wind-driven jar. It's just a vorticity balance interpretation. So, what Stommel did, this is the nice thing when you start a new field. There's everything to discover, okay? And well, if you're a very clever person, whatever you do then takes your name. So you have Sveggio balance, which was one of the first oceanographers, Ekman, Stommel, okay, all those famous oceanographers of the 30s and 40s, okay, and then we have Munk, okay, Walter Munk. Walter Munk actually died a month ago. Walter Munk is one of the most famous oceanographers in the world. He was an Austrian national. He was from Austria. Then I think his family escaped to the US during the Nazi period, and so he became a US citizen. And he was Munk was an astrophysicist, I think, yeah, I think he was an astrophysicist, or he started as a geophysicist. And then, as it happened during the Second World War, they got many physicists and mathematicians. They got them into the Navy and into the Air Force, and they want them to do meteorology, weather forecasting, or to start oceanography, especially for anti-war, anti-submarine war. Okay. So that's how actually oceanography got a boost in the 40s, because they took a bunch of meteorologists and they said, okay, now let's study the ocean and the structure of the ocean, the thermodynamics of the ocean, because we want to find the submarines and so on. And so Walter Munk started like that, and as a geophysicist, and he developed many theories, from surface waves to internal wave propagation, sound propagation in the ocean, using satellites to track waves in the ocean. And he developed one of the theories for the large-scale circulation. He was an amazing person. He started many fields in physical oceanography, and he died something like a month ago at the age of 102. And I saw him 2 years ago in a conference giving a talk at the age of 100. Amazing. It was more than a talk. More than a talk was a recollection of things he did. But he went to the conference. He took a plane, went to the conference, participated. Amazing. So Stommel, what Stommel did. So we're going to use the planetary geostrophic equations. Which is what we derived before for a Boussinesq fluid, and these are for the horizontal momentum. This is the hydrostatic balance and mass continuity. Okay, And we've derived this with the low or small Rossby number scaling. So Rossby number has to be much smaller than 1. And now if we take the curl of the horizontal momentum equation, or you cross differentiate the two, you just take the curl, you take the curl of that, okay, this is the curl of the horizontal momentum. Now you integrate over the full column of the ocean, because we want to get a solution for the whole column of the ocean, so we integrate vertically and the integral of the curl is just tau at the top minus tau at the bottom. Okay, so this is a vertical integrated solution for the horizontal momentum. Now this first term, the divergent term, it vanishes because we're using the dystrophic equations. So there's no vertical velocity. We are in a flat bottom, so there's no vertical velocity anywhere. And we're using a rigid lid. There's no sea level variability. Okay, so it's a rigid lid, flat bottom, there's no vertical velocity is 0 at the top, vertical velocity is 0 at the bottom. So the flow is divergent free, and so this is equal to 0. And so what we have is, this is beta, df by dy, this is the vertical integral of the meridional velocity, equal to the curl of tau at the top minus tau at the bottom. So this is again this Virgil balance, okay, just derived from the planetary dystrophic equations. So there is an input of vorticity from tau at the top or tau at the bottom, and that induces an advection, so a meridional velocity, an advection of planetary vorticity beta. It's just this Virgil balance again. Now, what is the contribution of Stommel is to work on this. We know what tau at the top is the wind stress curl, okay? But we don't know what the tau at the bottom is. How can we work on it? Is the Laplacian of pressure, not very useful, the vorticity of the dystrophic equation. So remember, we have a top Ekman layer where you have the curl of the wind stress, and we have a bottom Ekman layer where you have drag with the bottom, right? That's why you develop a bottom Ekman layer. You have the dystrophic vorticity working on top of the bottom Ekman layer, and that is balanced with drag with the bottom flow. So what Stommel did is to move this into the advection of planetary vorticity with an integrated meridional flow. That is going to be equal to a stress at the top, which is a function of x and y, minus what is happening at the bottom Ekman layer is drag. Okay? So let's use a linear drag to start with. And so here F at the surface is the curl of the wind stress. Okay, that's easy, yes.
According to Stommel, you're saying he uses drag at the bottom.
Mm-hmm.
But from the equation below, you say we have on the slip, we don't drag anything at the bottom, so we just slip.
Oh, vertical velocity is 0.
From the dystrophic balance.
I said the vertical velocity is 0. In the interior. Okay, this is the interior dystrophic flow. Okay, vertical velocity is equal to 0
So it's in the bottom.
in the interior. And then you need to add, this is what is happening in the Ekman layer. you have a wind stress at the top and you have something at the bottom. Okay, and so you need to add the curl of the wind stress at the top, which will create the vertical velocity, dz by dz, d by dz of w. Okay, and then something is happening at the bottom, creating the Ekman layer. Now we're adding the two pieces. So he took the Svergiu balance and said, okay, we have the advection of planetary vorticity, and then we have the curl of the wind stress at the top, and that will have to be balanced by something. Otherwise, you have input of momentum, and you have to balance the input of momentum somewhere. This is the vorticity of the geostrophic flow, which is what was driving the bottom Ekman layer, and R is going to be a linear drag. Okay, which can be Rayleigh friction, for example. Okay, it's just a linear drag, a parameter, which is going to be balancing the input of momentum at the surface. Okay, so this is the Stommel problem or the Stommel model. You give some input of momentum with a curl of a wind stress. That momentum is balanced by some friction at the bottom, and it induces a advection, meridional advection of planetary vorticity. So the interior flow is divergent free, we said this. So we can use a stream function as we derived the stream function before, because the interior flow is divergent free. So the Stommel model is beta curl of tau minus R okay, you use the stream function into the geostrophic flow and you get the Laplacian of the stream function. So the contribution of Stommel is actually adding the linear drag at the bottom, which will balance the input of momentum at the surface. Okay, so we got Svergiu balance, which is just a vorticity balance, and then Stommel added the linear drag at the bottom. Okay, so this is a picture of the depth integrated circulation. Remember, we're always talking about the depth integrated circulation. I think this is from a model. And this is just by using the Svergiu balance. Okay, the solution assumes depth integrated circulation vanishes at the eastern boundary. So you start integrating from 0 at the eastern boundary of the basin, and then you integrate the solution. You have to integrate this differential equation. So you start with psi equals 0 at the east, and you start integrating towards the west. Positive values, yellow and red, are anti-clockwise. So green values are clockwise. So this is telling you that the circulation is going like this, and it's going like this, right? And here is going anti-clockwise and anti-clockwise, right? So this is the Svergiu balance. I don't know if they used a linear drag at the bottom to compute this. But if you actually look at, if you compute the stream function from a model, the full stream function, this is actually not bad. Okay, just the Svergiu balance gives you the idea of the size of the gyres and the strength of the interior flow as well. Okay, so this is the wind-driven gyre in the North Atlantic, and this is the subtropical wind-driven gyre in the Pacific. This is the subpolar gyre, going the other way around, and the subpolar jar in the Atlantic. Right? The solution here obviously doesn't look much like reality. We'll see that the Svergiu balance doesn't apply in the Southern Ocean. But maybe it's difficult to see, but there is something that we will get to this next time, or maybe in 2 classes time. Okay, there is something that is missing in these wind-driven gyres. Look at this wind-driven gyre, and look at this wind-driven gyre. The solution is, so if you actually look at the those lines, of course, are lines of constant stream function, right? That's the stream function. If you look at, let's say, for example, the North Atlantic, okay, you have lines that go like this. This is the -5. You have a line like this. This is the -10. A line like this. This is the -15. And something like this. This is the -20. Right? And they start from 0 at the eastern boundary. So psi equals 0 at the eastern boundary, and then you start integrating towards the west. And as you approach the west, it goes like this, right? So, and the same thing in the Pacific, basically. So first you see something here that is telling you that the Svergiu balance is in place. You have a wind stress curl, and the wind goes like this, so you have a vertical velocity into the ocean. The column shrinks, okay, and it has to conserve angular momentum. It's not going to change relative vorticity, it's going to change planetary vorticity. And it's going to change planetary vorticity by moving towards the equator. F diminishes. We're shrinking the water column, so we'll have to diminish its vorticity. And it will do that not by changing relative vorticity, but by changing planetary vorticity. So F will decrease. And so you will start going towards the equator. We will say this again and again. Okay? And so you see in those lines of constant stream function that all these lines are basically moving south. This is the depth integrated velocity, V. And so the input of momentum by the wind stress, this input of momentum by the wind stress is generating a depth integrated velocity, meridional. And so you see that basically the whole North Atlantic or North Pacific is moving to the south. You see all these lines, -5, -10, -15, they're basically at the same longitude, and they're just going down to the south, right? Going to the south, going to the south, going to the south. And then they close the gyre. Yeah?
See them.
You don't see them.
Going to the south.
So green is clockwise, okay? So the circulation is clockwise. So this is telling you that the stream function is going like this. Okay? So it's not. So you see that all those lines are basically the -5 is going like this and then south and then closing. The -10 is going east, south, and then closing. The -15 is going like this, and the -20 is going like this, right? So all the flow here is directed towards the equator, and it's the depth integrated meridional velocity. So basically the whole North Atlantic is moving towards the equator. So V is negative. So beta is diminishing. Okay? So you're changing planetary vorticity for balancing the input of momentum by the wind stress. You have input of momentum by the wind stress. Do you change relative vorticity or do you change planetary vorticity? We'll see that the large scale flow doesn't change relative vorticity. The large scale flow changes planetary vorticity. We will see that in a second. So F is changing. It's not the relative vorticity that is changing. And so beta is changing and is creating a meridional advection.
It increases the equity.
F is changing. So you're moving towards the south in order to balance the input of momentum at the surface. What you need to change is the planetary vorticity. The planetary vorticity is F. Right? So do you change F or do you change relative vorticity? We will see in a second that the large scale circulation doesn't change relative vorticity. It doesn't start spinning faster or slower in the place. It changes F. It changes the planetary vorticity. So F will change. The particle will move to the north or it will move to the south in order to change the planetary vorticity. In this case, it's moving to the south. So it's changing F by moving to the south in order to balance the input of vorticity at the surface. And you see that the whole North Atlantic and the North Pacific, the center of the gyre, is directed to the south. So basically the solution here is in Sverger balance.
So in this case, we are neglecting the effect of the boundary conditions.
Exactly.
On the lateral boundary.
Exactly. So there is a problem there. If you look at the string function, they hit the continent. This is not physical. Okay? This is just a mathematical solution. You're integrating the differential equation with the boundary condition psi equals 0 at east, and then you start integrating to the west. And you get this solution. This is the Sverger balance. There's something missing. You're missing the Gulf Stream. You're missing the boundary currents on the west. You're not closing the gyre here. Okay? You have an input of wind stress at the surface, which I think in this case is balanced by some linear drag at the bottom. Okay? But if you look at all those streamlines, they hit the coast. Okay? This is not physical, it's not realistic. It's not the complete solution of the flow. There is something missing. Okay? What you miss is something here that closes the gyre in a physical way and conserves mass and conserves energy. Okay. This is just the Sverger balance, which is valid for the interior. So the interior is in Sverger balance. And the interior responds by changing planetary vorticity. Something else is happening here that is not taken into account in this theory. Yeah?
So if, for example, we are talking about relative to small,
I don't think the video is being uploaded yet.
The video has not been up. The video
Talking about the recordings.
has not been uploaded yet. I don't know. So instead of working with the planetary isotopic equations, remember we used a flat bottom ocean, a homogeneous ocean. So we could actually work with a homogeneous model. Well, I have 10 minutes, so I'll just show you this. Okay, we can just work with the homogeneous model instead of taking the planetary isotopic equations and then vertically integrate them. We can just start with a homogeneous layer of fluid of depth h. Okay. You use the shallow water equation. I'm sure you did this in atmospheric dynamics in GFD. You take the shallow water equations, and the potential vorticity equation for the shallow water equation is just the Lagrangian derivative of planetary vorticity plus relative vorticity is equal to some F over H. H is the total depth of the fluid column. And F, you have both the forcing and the friction. If the ocean is flat bottom, H is a constant. And so you have the Lagrangian derivative of the relative vorticity plus the beta V equal to some forcing and friction. Okay? So you just start with the potential vorticity equation of a homogeneous layer. And this is just the barotropic PV equation. You've seen this in atmospheric dynamics. You can derive wave properties from this. We use a homogeneous model, flat bottom and rigid lid. So the flow is again divergent free. We can use again the stream functions, and you have d by t of the Laplacian of the stream function plus the meridional velocity due to beta equal to some curl minus the Rayleigh friction at the bottom. Okay. This is exactly the Stommel model, but now we have the Lagrangian derivative. So there is a time dependent and there is an advective nonlinear term. Okay. So this is the full Stommel problem. Remember at the beginning I said we're going to use homogeneous model, steady state, and the beta plane approximation. Here there's no steady state. This is the time dependent. You have a d by dt, and you have a nonlinear term, the u d by dx of u. Okay. So you can get the time dependent nonlinear Stommel problem just by starting with the PV equation. The steady nonlinear model is simply by saying that d by dt is equal to 0, and then you recover the steady solution of the Stommel problem, and the solution is just the equation 4.43. You have the Jacobian upside, Laplacian upside, plus the usual Stommel problem. Okay? And you just use the Jacobian here. So this is the steady nonlinear model, which you can use in order to produce that picture. Instead of having the steady linear solution, you can do the steady nonlinear solution of the Stommel problem. If you want to recover this Stommel model, you just ignore the advective derivatives or the nonlinear terms, and you recover the simple Stommel solution. Okay? Now, if you take the, now I'm going to get to your question. You take the PV equation, which is there, and you do a scale analysis. Okay? This is U over L and U over L, and this is beta U. Okay? Then you defined a value for vorticity, Z equal U over L. So when can you ignore nonlinearities is when the Z, the vorticity, is much smaller than beta L. Okay? Or in other words, so this is U squared over L squared, beta U, so you get rid of this, you get rid of this. So this is Z beta L. Yes. So you can ignore nonlinearities when the vorticity, the scale for the vorticity Z, is much smaller than than beta. Okay? In that case, you can ignore the nonlinearities. Or in other words, if you come from here, u over L square beta, this is what we call the beta Rossby radius, okay? Or the beta Rossby number. Assuming that beta, the Rossby number, is much smaller than unit, that is equivalent to doing the small Rossby number assumption that we did at the beginning to recover the planetary Justov equations. Okay. So when the beta Rossby number is much smaller than 1, then nonlinearities are not important, and you can just use the simple Stoney model. Okay, so your question was actually this. So how does the ocean respond to an input of vorticity? And what is really changing? The response to an input of vorticity is a relative vorticity or planetary vorticity that will respond. Okay. So you have the PV equation. You do the scale analysis as before, and you see that the ratio of the relative vorticity and the advectional planetary vorticity is the beta Rossby number. Okay, and so when the beta Rossby number is much smaller than 1, then relative vorticity is not important. When the beta Rossby number is close to 1, then the relative vorticity is important. So let's see a couple of cases. So the Bayesian scale, you remember what we were looking at before, it was something like this. So let's look at the Bayesian scale, the interior. Okay. We have scales that are roughly 1,000 kilometers, and then velocities which are very, very small, 0.01 meter per second. Then what is the beta Rossby number? This is 10 to the minus 2. Beta, remember, was 10 to the minus 11. L is 10 to the 6, but it's L squared, so this is 10 to the 12. So this is 10 to the 1, 10 to the minus 3. So the beta Rossby number is much smaller than 1 in the interior. So if the beta Rossby number is much smaller than 1, then relative vorticity is much smaller than planetary vorticity. So this is saying that within the Bayesian scale, so here, the rate of change of relative vorticity is much smaller, the Lagrangian derivative of relative vorticity is much smaller than the rate of change of the planetary vorticity. So if we have an input of vorticity, this wind stress at the surface, for example the wind stress, the flow will not start to increase its rotation, relative vorticity will not change. What will change is planetary vorticity. Okay. And so the flow will start to move meridionally and balance the input of vorticity with a change in F. This is what is happening at the large scale, where the beta Rossby number is much smaller. Now consider a frontal zone, a boundary layer, for example here, okay, that is, for example, tens of kilometers, and the velocity is much larger, 0.1 meter per second. Okay, it's much larger, obviously, because you have to conserve mass. All this water coming down has to come up on a tiny boundary layer, so it will move much faster, and the streamlines are much closer together. So on a frontal zone, on a boundary layer, the scale is much smaller and the velocities are much larger. So in that case, what do we have? 10 to the minus 1 for the velocity, 10 to the minus 11 is beta, and that is it 10 kilometers? Yeah, okay. 10 to the 4th, which is to the squared, 10 to the 8th. So this is 10 to the minus 3, 10 to the 2nd. So on a frontal scale, the beta Rossby number is much larger than 1. So the change in relative vorticity is much larger than the change in planetary vorticity. So on a frontal scale, on a boundary layer, if you have an input of vorticity, the flow will not respond by changing planetary vorticity. The flow will respond by changing its relative vorticity. And so actually, in this large scale, F will change, and in this frontal scale, relative vorticity will change in order to balance the input of vorticity. Here you have an input of vorticity, and it's balanced by F. So F changes, and so the flow moves meridionally. How is to the same input of vorticity, how is the flow in this boundary layer responding? By changing relative vorticity. And we will see how that implies a meridional velocity. Was that your question?
Sure. And then I'm wondering what's happening at the boundary.
Now you're wondering what's happening at the boundary? Yes, you will see that.
It's moving at speed.
No, then you need to add friction here. You add friction, and so you have friction with the boundary, and this will change the relative vorticity of the flow.
So this is valid for the oceans only, or for both the atmosphere and the ocean?
Well, so these values are good for the ocean, they're not the same for the atmosphere. So the planetary geostrophic equations are not used in the atmosphere because the scales are totally different. So you use the beta plane approximation, but you don't use the planetary geostrophic equations. They're not good for the atmosphere. They're good for the atmosphere only if you look at Rossby waves, very large scale flows.